This video is going to cover limiting reactants and percent yield. Now, limiting reactants is simply the substance in a chemical reaction that runs out first. It seems very simple, but it's something that tends to confuse a lot of people. So to help you better understand, I'm going to use a cheesy, no pun intended, example. Let's say I want to make a cheese sandwich. I can say that for every 2 pieces of bread, there will be 2 pieces of cheese, and those two together will produce 1 sandwich. Now, if I have 92 pieces of bread and 86 pieces of cheese, how many sandwiches can I make? Now, to answer this question, we need to figure out which ingredient we're going to run out of first. So we can use dimensional analysis to answer this question. So if I have 92 pieces of bread, how many sandwiches will that make? We can answer that question by using the molar ratio of bread and sandwiches. So for every 1 sandwich, there are 2 pieces of bread. Now 92 times 1 divided by 2 is 46. So our units cancel out here, bread and bread cancels out, and the unit we're left with is sandwich. So we can make 46 sandwiches. Now let's do the same thing for cheese. If we have 86 pieces of cheese, how many sandwiches can I make? So we'll do the same thing. We'll use the molar ratios between sandwiches and cheese. So for every 1 sandwich, there are 2 pieces of cheese. Our units of cheese cancel out. 86 times 1 divided by 2 is 43. So we can make 43 sandwiches. Okay, so if we look at what we have here, we see that from 92 pieces of bread, I can make 46 sandwiches. And from 86 pieces of cheese, I can make 43 sandwiches. So what is the maximum amount of sandwiches that I can make from my 2 ingredients here? The maximum amount of sandwiches we can make is 43. And it's 43 because I don't have enough cheese to make 46 sandwiches. I only have enough cheese to make 43 sandwiches. Therefore, that makes cheese the limiting reactant. And I'll abbreviate that LR. It's the ingredient that's going to run out first. Now, that would mean that we have bread. Bread is an excess, meaning that we have more than enough bread to make 43 sandwiches, but we don't have enough cheese to make 46. So the maximum amount of sandwiches we can make is 43, because we only have enough cheese to make 43 sandwiches. That makes cheese the limiting reactant and bread the excess reactant. Now, what did we have to do to be able to compare bread and cheese? Well, we had to turn them into the same thing. And in this case, we turned them both into sandwiches. That's the only way we could accurately compare these 2 ingredients. So we had to take bread and cheese, which are 2 different ingredients, and turn them into something of the same. And so in this case, the same thing is sandwiches. So that's how we could tell which is the limiting reactant. So in chemistry, we do the exact same thing. Here's an example of a limiting reactant question. The question says, how many moles of NH3 can be formed from 3 moles of N2 and 6 moles of H2? What is the limiting reactant? Now, just as we started off doing the stoichiometry problems by identifying what we're given and what we're being asked to find, I like to do the same exact thing when we start limiting reactant problems. So let's take a look at what we're given in this problem and what we're being asked to find and make a note of that under the given reaction, and that can help us get started, especially if you're stuck and don't know what to do. So the first thing I see in the problem here is that we're told that there are 3 moles of N2. So I'm going to go ahead and write this underneath the equation. So 3.0 moles of N2. Now we're also told that we have 6 moles of H2. So I'm going to write that under the H2, 6.0 moles. Now the question here says, how many moles of NH3 can be formed? So that tells me that we are looking for an amount of moles of NH3. So I'm going to put a question mark and put moles to let me know I'm looking for how many moles of this substance. Now, if you remember when we were doing the sandwich example, we took 2 different ingredients and we turned them into the same thing, which was sandwiches, to accurately compare to see what is the maximum amount that we can make, and that told us what ingredient we ran out of first. So in chemistry, we do the exact same thing, but like how we use sandwiches in the first example, we're going to use moles in chemistry. So if we have 2 different reactants here, N2 and H3, we can turn both of these reactants into moles of NH3 and compare those amounts to see what is the maximum amount of moles of NH3 we can make, and from that, what the limiting reactant is. So we have 2 goals for this problem. The first goal is to turn our moles of N2 into moles of NH3. The second goal is to turn moles of H2 also into moles of NH3. And if we can do that, we'll be comparing sandwiches to sandwiches. So moles of NH3 to moles of NH3. And that will tell us what is the limiting reactant. So we're trying to find out if we have 3 moles of N2, how many moles of NH3 will that produce? Also, since we have 6 moles of H2, how many moles of NH3 will that produce? So that's what we're going to do here. So let's start with N2 first. The question tells us that we have 3.0 moles of N2. Now, if we want to convert that into moles of NH3, we're converting moles of one substance into moles of another substance. So moles of A into moles of B. Now, if you don't remember how to do that, you need to go back and watch the stoichiometry video, because I go into a lot of detail about how to convert moles of one substance into moles of another substance. So if you do remember how to do that, we convert moles of something into moles of something else by using the molar ratio of those 2 substances. So if we're looking at N2 and NH3, what is the molar ratio? So the molar ratio would be 1 N2, which I'm going to put in the denominator since we want N2 to cancel out. And then on the top, I'm going to put 2 NH3. Now if we cancel out our units, N2 cancels with N2, and 3.0 times 2 divided by 1 gives us 6.0. What are we left with? We're left with moles of NH3. So moles of NH3. And that was our first goal up here. We took moles of N2 and we converted them into moles of NH3. Now we need to do the same thing with H2. The problem says that there are 6.0 moles of H2, and we need to convert that into moles of NH3. So again, to do that, we use the molar ratio. So the molar ratio between H2 and NH3 is 2 NH3 over 3 H2. And I'm going to put H2 in the bottom because that's what I want to cancel out. And again, if you have no idea what I'm doing right now, go back and watch the stoichiometry video. In the beginning, I talk about molar ratios, and that should fill in the gap on what I'm doing here. Okay, so H2 cancels out with H2, and we're left with moles of NH3. Now, when you put this into your calculator, we should get 4.0 moles of NH3. Okay, now we're looking at the same units here. We have mole of NH3 and moles of NH3. So by looking at these two numbers, how do I tell which is my limiting reactant? Well, just like when we looked at our cheese sandwiches, the smaller number, I think it was 43, was the maximum amount of sandwiches we can make. So again, in this case, the smaller of the two numbers is the maximum amount of NH3 we can make. Now the smaller of these two numbers is 4.0. So 4.0 is the maximum amount of NH3 that we can make, which answers this question right here. How many moles of NH3 can we make? Now what produced that amount of NH3? The reactant that produced that amount of NH3 was H2 right here. So 6 moles of H2 gives us 4 moles of NH3. That means that H2 is our limiting reactant because it can only produce 4 moles of NH3. N2, on the other hand, will be considered in excess because there's enough N2 to get to 6 moles of NH3. But we don't have enough H2 to get to 6 moles. We only have enough H2 to get to 4 moles. That's why H2 is our limiting reactant and N2 is our excess. So now we have both parts of this question answered. What is the limiting reactant? The limiting reactant is H2 because H2 produces the smaller number, the smaller amount of moles of NH3. So therefore that makes N2 the reactant that is in excess. Let's try a problem that gives us grams of two reactants because that is the unit of measurement that we work with in a lab. This question says there are 150 grams of H2 and 1500 grams of O2. How many grams of H2O can be produced? Which reactant is limiting and which is in excess? So again, I like to start off by just identifying what we're given and what we're being asked to find. So I see here that we are told that there are 150 grams of H2. So I'm going to write that underneath H2, 150 grams. And there are 1500 grams of O2. So I'm going to write that underneath O2, 1500 grams. And the question says, how many grams of H2O can be produced? So I'm going to put a question mark with a G for grams, telling me that I'm looking for an amount of grams. So which reactant is limiting and which is in excess? Okay, so we need to look at these two amounts, these two reactants here, and see how much of the product of H2O can they make. So 150 grams of H2 can make how much H2O, and 1500 grams of O2 can make how much H2O. So in the other problem, and like in the cheese sandwich problem, we converted our two different reactants to the unit to be the same product. So we're going to do the same thing here, except since we're given grams, we're starting out with grams, we have to convert everything to moles and then to moles of H2O. So here is the process that we need to follow. So first we need to do grams of H2 into moles of H2, and then moles of H2 into moles of H2O. And that'll take care of the first reactant. Then our second reactant, which is O2, we are starting off with grams of O2, and we have to convert that into moles of O2. Then for moles of O2, we have to convert that into moles of H2O. And that way, we'll be comparing the same thing. Sandwiches to sandwiches, moles of water to moles of water. Now, if you're not sure why we have to go from grams to moles first, and then moles of substance A to moles of substance B, you should go back and again watch the stoichiometry video. So really, the point is, in order to be proficient at limiting reactant questions, you need to be proficient in stoichiometry. Okay, so let's get started. Let's start off with H2. So the problem says there are 150 grams of H2. And we need to convert that into moles of H2. So how do we convert grams to moles? We convert grams to moles by using the molar mass. So in 1 mole of H2, there are 2.02 grams. Now, for our units, grams cancels with grams, and we're left with moles. Sorry, there's supposed to be an H2 in here. So we're left with moles of H2. So when you put this into your calculator, you should come up with 74.2 moles of H2. Okay, so that took care of this part of the first goal. Now we need to look at this part, moles of H2 to moles of H2O. So how do we convert moles of substance A to moles of substance B? We do that by using the molar ratio. So the molar ratio in this case is going to be 2H2, which is going to go on the denominator because I want H2 to cancel out, and 2H2O on the top because that is the unit that I want to keep. So H2 is going to cancel out with H2, and I'll be left with moles of H2O. So when you do that, we should come up with 74.2 moles of H2O. Okay, so we went from grams of H2 to moles of H2O. So we took care of the first goal. Now we need to go through the exact same process with O2. The question says we have 1,500 grams of O2. We need to convert that to moles by using the molar mass of O2. So in 1 mole of O2, there are 32 grams. Now, grams is going to cancel with grams, and we're left with moles of O2. So that comes out to 46.8 moles of O2. Okay, so that took care of this part of the goal. Now again, we need to take care of this part, moles of O2 to moles of H2O. And we do that by using the molar ratio. So there are 2 moles of H2O for every 1 O2. Our O2 cancels with O2, and we're left with moles of H2O. So when you put that into your calculator, you should get 93.7 moles of H2O. Okay, perfect. So again, we started off with grams of O2, and we ended up with moles of O2, so we completed that second goal. Now we have the amount of our 2 reactants in the same unit. We have them both in moles in terms of moles of H2O, moles of water. So now we look at these 2 amounts of moles, and the smaller number is our limiting reactant. So out of these 2 numbers, 74.2 is the smaller number, meaning that is the maximum amount of moles of water that we can make. Now, which reactant produced that amount of moles of water? H2. Since H2 produced the smaller amount of moles of our product, that means that H2 is our limiting reactant. And since H2 is the limiting reactant, that means that O2 is what's in excess. So we have enough O2 to make 93.7 moles of H2O, but we don't have enough H2 to make that amount. We only have enough H2 to make 74.2 moles. So that is why H2 is our limiting reactant, because H2 is the reactant that's going to run out first once this reaction actually takes place. So did we answer the question? We identified what the limiting reactant is and which reactant is in excess, but we didn't totally answer the question in regards to how much water can be produced. We identified the maximum amount of moles of water that can be produced, but the question is asking for how many grams of water that can be produced. So the next step in this question is to convert the maximum amount of moles of water into grams of water. So we're not concerned with this many moles of water because we can't make that much. We don't have enough H2 to make that amount of moles of water. So we're not even going to look at it. We're only going to look at the 74.2 because that's the maximum amount that we can make. So I'm going to scroll down a little bit. And so if the maximum amount of water we can make is 74.2 moles of H2O, we need to convert this to grams of H2O. And we do that by using the molar mass of water. So we put moles on the bottom because that's the unit we want to cancel out. And in 1 mole of water, there are 18.02 grams. And again, we figure that out by figuring out the atomic mass of water and then just writing it in this grams per mole unit. Okay, now in terms of units, moles cancels with moles, and we're left with grams of H2O. So when you put this into your calculator, you should come up with 1,338 grams of H2O. And that is the answer to the question, because the question is asking how much water in grams can be produced. Here's a question from your group problems that gave a lot of people some trouble because there are actually 2 different ways to solve this limiting reactant question. The question says, if 1 gram of sodium bicarbonate reacts with 1 gram of citric acid, which is the limiting reactant? So if we approach this just like we have any other problem, we see we're given 1 gram of sodium bicarbonate and 1 gram of citric acid. So I'm just going to write that under each of these reactants. So I'm given 1 gram of this and 1 gram of this. Now, right off the bat, you can probably see that this is different from the previous 2 questions we did because we're not asked to find how many grams of one of the products can be made based upon the limiting reactant. So if we're not asked to find how much of a product we can make, how do we do this question? Well, the answer is that because of the molar ratios, it doesn't matter which product we pick. So we can actually relate 1 gram of both of our reactants to any of the products. You can pick any one you want. So to show you that this works, I'm going to pick water, but I could have just as easily picked one of these other 2 products and it would have worked out the same. So since I'm picking water, my question then becomes 1 gram of sodium bicarbonate can produce how many moles of water? And likewise, 1 gram of citric acid can produce how many moles of water? So since those are the goals that I'm trying to do, I'm going to come over here and just write a little flow chart so I know the steps that I have to take. So the first thing that I have to do is to convert grams of the sodium bicarbonate, which is NaHCO3, and I have to convert that to moles of NaHCO3. Then I have to convert that to moles of water because that is the product that I picked. But again, if you want to pick one of the other products, you can do that and you will get the same exact answer. Now, I have to do the same thing with the citric acid. So we're given grams of H3C6H5O7, and the first thing we need to do is to convert that to moles of citric acid. So moles of H3C6H5O7. And then after that, we need to convert it to moles of H2O. Because then we will be comparing the same thing, sandwiches to sandwiches, as I like to say. Moles of water to moles of water. Okay, so let's get started. Let's take our grams of the sodium bicarbonate first and convert that to moles of sodium bicarbonate. So 1 gram of NaHCO3, and we want to convert that to moles. So we use the molar mass. So in 1 mole, you would have to take a second to figure this out. You know, it's a side step you have to work out, but it's important. So there are 84.01 grams. And now for our units, grams cancels with grams, and we're left with moles of sodium bicarbonate. So when you put that into your calculator, you should get 0.0. And try to use 4 significant figures on these intermediate steps. I know I've said it before, but with 4 significant figures, you usually won't have any rounding errors. So 0.01190 moles of NaHCO3. Okay, so we did this step right here, grams to moles. Now we need to convert moles of sodium bicarbonate to moles of water, which is the product that I picked. And we do that by using the molar ratios. So what are the molar ratios between these two substances? There are 3 NaHCO3 to every 3 waters. Now because 3 over 3 is basically 1 over 1, the number is going to be the same, but our unit's going to change. NaHCO3 cancels with NaHCO3, and we're left with moles of water. So our answer is going to be the same. It's going to be 0.01190 moles of water. Okay, so we took care of this first part. We started off with grams of sodium bicarbonate, and we ended up at moles of H2O. Now we're going to do the exact same thing with citric acid. So the question says there is 1 gram of H3C6H5O7, and we need to convert that to moles by using the molar mass. So in 1 mole of citric acid, there are 192.14 grams. Now, if we look at our units, grams cancels with grams, and we're left with moles of citric acid. So this number comes out to 0.005204, and the unit is moles of H3C6H5O7. So again, that took care of this step, going from grams to moles. And now we need to do this step, going from moles of citric acid to moles of water. And we do that by using the molar ratio between the two. So again, we put 3H2O on the top because that's the unit we want to retain. And we put 1 of the citric acids on the bottom because that's what we want to cancel. Now, when we look at our units, citric acid cancels with citric acid, and we're left with moles of water. So when you put this into your calculator, I'm going to zoom in here so I can write it, squeeze it in. We end up with 0.01561, and that's moles of H2O. Okay, so now we also completed the second step because we started off with grams of citric acid and we ended up with moles of H2O. So now if we look at these two numbers, the way we tell which one's the limiting reactant is whichever one is smaller. So between these two numbers, this one right here is smaller. So this is the maximum amount of water that we can produce. Now, which of the two reactants produced this amount of water? This one right here, the sodium bicarbonate. Therefore, the sodium bicarbonate is our limiting reactant. Because if we look at the citric acid, we have enough citric acid to produce this many moles, but we don't have enough sodium bicarbonate to produce that many moles. We only have enough sodium bicarbonate to produce this many moles right here. Therefore, and this is the smaller number, therefore sodium bicarbonate is our limiting reactant. So that's one way you can answer this question. You're given two amounts of reactants. You can choose any of these products to turn it into, and you will get the same limiting reactant every time. But now I want to show you a different way to solve this same question. So I'm going to erase, actually I'm just going to copy the equation here and move down so we can compare our numbers at the end. So I'm going to put this right here. Oh, captured some extra stuff here. Let me erase all this. Okay. So again, in this question, we're only given the amount of grams of the two reactants. Now, it doesn't matter what we turn the reactants into. In the previous questions, we've been choosing a product to turn the reactants into. The important thing is that the reactants are turned into moles of the same thing. So another option we have when doing limiting reactant problems is we can choose one of the reactants to turn both of the reactants into. So for example, I can choose to turn both of our grams of both of our reactants into moles of sodium bicarbonate, or I can choose to turn grams of both of our reactants into moles of citric acid. So I'm going to pick sodium bicarbonate, and I will show you how to do this problem, this second way of limiting reactants, using sodium bicarbonate. But again, you could choose citric acid and you will get the same exact answer. So if we put a little, map like we did for the other problems, we're going to take grams of grams of sodium bicarbonate, which is NaHCO3, and we're going to turn it into moles of sodium bicarbonate, NaHCO3. Now we're going to do the same thing with citric acid. We're going to take grams of the citric acid, which is H3C6H5O7, and the first step, if we ultimately want to turn it into moles of sodium bicarbonate, before we can do that, we have to turn it into moles of citric acid. So we have to go from grams of citric acid to moles of citric acid. And this is just following the stoichiometry roadmap. So if you need to, write down a copy or go back and refer to a copy of that roadmap, and it will make the order of these steps a little bit more clear. So after we go from grams of citric acid to moles of citric acid, we can then, let me move this over a little bit, we can then go to moles of the sodium bicarbonate. So we'll still be able to get to the answer of limiting reactant because we're comparing moles of sodium bicarbonate to moles of sodium bicarbonate. We're comparing sandwiches to sandwiches. Okay, so now let's see how to figure this out. So I'm going to start with sodium bicarbonate first because that is a much simpler, there's only one step here. We just have to take it in grams and turn it into moles. So we have 1.00 grams of NaHCO3, and how many moles does that make? Well, we just figure that out by dividing by the molar mass. So 1 mole of sodium bicarbonate, we divide that by 84.01 grams. Now if we look at our units, grams cancels with grams, and we're left with moles of sodium bicarbonate. And when you put that into your calculator, you get 0.01190, and the unit here is moles of sodium bicarbonate. Okay, so this is the amount of moles that we can make from what we have. So we have 1 gram. I didn't do any kind of molar ratio here. I just took the amount of grams we were given and converted it into the amount of moles that we were given. So this is the amount of moles of sodium bicarbonate that we actually have. So now I'm going to do this second part down here and convert our citric acid into moles of citric acid, and then moles of citric acid into moles of sodium bicarbonate. So let's do that. So we have 1 gram of citric acid, H3C6H5O7, and we need to convert that into moles of citric acid. So we do that by finding the molar mass, which is 192.14 grams per mole. Okay, now we need to cancel out our units. Grams cancels with grams, and we're left with moles of citric acid. And when you put this into your calculator, you should get 0.005204 moles of citric acid. Okay, so now again, this took care of this part of our little flow chart here. Now we need to do this part, going from moles of substance A to moles of substance B, which we do by using the molar ratios from the coefficients in this balanced equation. So there are 3 sodium bicarbonates to every 1 citric acid. Now when you put this number into your calculator, you should get 0.01561, and the unit on this is moles of sodium bicarbonate. I'm going to move this over a bit so I have some more space. NaHCO3. And the unit is correct because citric acid cancels out with citric acid, so we're left with moles of sodium bicarbonate. And so this is the amount of moles that's required to make this reaction occur. So again, if you look at the two numbers, we now have both of our reactants in terms of moles of sodium bicarbonate, moles of NaHCO3. We look at to see which number is smaller. This number is smaller. And the number that is smaller is our limiting reactant. So what produced our limiting reactant? NaHCO3 produced our limiting reactant. Therefore, NaHCO3 produced the smaller number. Therefore, it is the limiting reactant. So if we compare the numbers that we got doing it this way by taking the two reactants and turning them into one of the reactants, in this case sodium bicarbonate, you'll see that it's the exact same numbers we got by doing it this first way up here. So comparing this right here to the moles of water to the moles of sodium bicarbonate. So this works out because of the molar ratios. All the numbers in these equations are related, so you could really, it's really up to you which way you decide to solve these types of problems. You can either take both reactants and turn them into one of the products. It doesn't matter which product, but if the question's asking you how much of a certain product can be made, it is wise to choose that product for your conversion so that you are solving both parts of the question at one time. Or if the question is not asking how much of a product is going to be produced, it's just asking you to identify the limiting or excess reactant, and you're just given two amounts of reactants, you can solve it the second way by choosing to turn both reactants into moles of one of the reactants. So I hope that wasn't super confusing. I just wanted to show you guys that there are two different ways to solve limiting reactant problems.